Okay, so here we have a problem involving drag force, and some other concepts here and there, but it's really based around how the drag force works, and it's a pretty old question, but it's still a good one. So we have a block with an initial speed, and it's moving on a horizontal surface, and we're not told it's frictionless, so we should assume it has friction. The first question is simply, how much work must be done to bring it to rest? We don't know anything about the force yet, so we don't want to make any assumptions there. So the first thought you might have, right, is for this part is to use W equals F d cosine theta, right, something like that. But we don't know anything about this or anything about this. And I mean, I guess since we know it's probably friction, we know a little bit about the angle, but we don't know anything about most of that, so we can't really do it that way. But we do know something about our energy, right? Our initial energy is 1/2 m v naught squared, and our final energy, since it's at rest and it's on a horizontal surface, must be 0. And so really the way we want to get it work is not from a direct calculation of the work in terms of what does it, but in terms of the change in energy, right? Delta E equals W. And we just wrote the energies that we have, so delta E is is going to be 0 minus 1/2 m v naught squared, and that must equal to W, and so the work must be negative 1/2 m v naught squared, right? So the biggest mistake you can make on this one is just trying to use this equation, because you don't know enough about that yet. Now that we know the work, we're going to use that one to figure out the force, but if we knew the force, we could use that to get the work. Right, so you got to use what you have. So that's part A. The work, first of all, it is negative, right? We lose energy, so it is negative work. That's another important point. All right, so part B. Now we're told a little bit about the force, right? Force is negative k times v. Right, so this is a force that's directly proportional to its velocity, and all k is just a constant. We don't know anything about it, but it's relates how it's the constant proportionality relating the velocity and the force. So we need to write the acceleration in terms of m, k, and v. Well, all we really know in terms of this, or to relate forces and accelerations, is F equals ma. So a equals F over m. And we just wrote what the only force is, right? It was negative kv divided by m. And so that's part B. We've written A in terms of kv and m. Right? Notice again that negative is there. So part C is where the problem starts to get a little bit tricky. Right? So we do part C. If we want to figure out the speed as a function of time, the first thing we have to remember that's going to help us solve this problem is the relationship between acceleration and velocity. Right? Since A equals dv dt, we can rewrite that part B result as dv dt equals negative k over mv. And this is a differential equation you have to be able to solve. Right, this is the separation of variables approach. So that's what we're going to do next. We're going to separate the variables into all the velocity stuff on one side and all the t stuff on the other. So we divide by v and multiply by t. Right? And now we have to integrate. So we integrate this side and integrate that side. So on this side, we get a natural log. And on this side, we just get t. And we need to remember that constant of integration, because we haven't put endpoints on our integral. So now we need to find this constant c for using our initial conditions. So we are told at t equals 0, its velocity is v0. So plug those numbers in. Right? So this term cancels, because it's just times 0. And we find that c must be that, ln v0. Okay, so now we can start actually solving. So we get ln v0, or sorry, oops, go back to our original equation. ln v Right, that's what we now found. And now we need to solve for v equals, which means we need to do we need to exponentiate both sides, right? E to the that and e to the that. So this is v of t now. So e to the negative k over m times t. We have e to the natural log of v0, which is just multiplying by v0. Right? And so we can rearrange that to get v of t equals v naught e to the negative kt over m. Right? And that has the characteristic shape that you should expect. Right? It's an exponential decay, so as time goes on, it slows down. And again, if you can't do that whole integral, you should be able to do this setup at the very least, and at least get a start on it. But you should be able to do this separation of variables process, and it's important. All right, part D. So we want to know the total distance the block slides. And so to do this, we really need the position as a function of time, right? Because we know that the velocity, right, velocity as a function of time is going to look something like that. So, right, as t goes to infinity, v goes to 0, right? So that means that after an infinite amount of time, that's the total distance the block will have traveled. So if we knew x of t, actually let's write it formally, t goes to infinity. That's terrible, infinity. There. Then this would tell us the final position, right? We start at x equals 0, and we end up at x final. So we really need x of t and then evaluate it at t goes to infinity. So we have v of t. We want to get x of t, so we have to integrate. Right? X of t equals the integral of v of t dt. Right? So we write that. And this is a pretty easy integral because it's an exponential. Right? So the v naught stays. We get a negative m over k, e to the negative kt over m. Right? And then we have to add the plus c for the constant of integration. So now, at t equals 0, we're going to say it's at x equals 0. So to solve for c, we get 0 equals v naught m over k e to the 0 plus c, right? Which tells us that c equals m v naught over k, right? Because e to the 0 is 1, then we move to the other side, so that gets rid of the negative. Okay, so now we know x of t. Right, so let's put a little space here. So we can factor out that m v naught over k. We get 1 minus e to the negative kt over m. Right? That's factoring out, this term I factor out all of it, so there's the 1 left over. We have a negative sign there, so that's why it's 1 minus. Okay? So then we evaluate this as limit t to infinity. And in that limit, this becomes 0, so we're left with x goes to m v naught over k, and so that's the total distance that we travel.